Hello, I welcome you all in this presentation related with the subject materials processing, fundamentals and practical. In this particular presentation, I will be talking about the need of the heat treatment in metal forming process. In the metal forming process, we can do the forming below the recrystallization temperature, which is called as a cold forming or warm forming or hot forming above the recrystallization temperature. So, when the metal is subjected to the plastic deformation, there will be lot of changes in form of directionality in terms of the grain orientation in particular direction, anisotropy, and even localized plastic deformation leads to the development of residual stresses. So, the plastic deformation, whether it is done at a higher temperature or low temperature, brings in the heterogeneity in terms of the microstructure, mechanical properties and the residual stresses. Therefore, sometimes it becomes important to carry out the thermal treatment of the metal formed components to restore the properties, to bring the homogeneity in properties, to eliminate the residual stresses or to minimize the residual stresses, so that the performance of the component can be enhanced. So, in this particular topic, we will be talking about the various aspects. The first is the need of the thermal treatment or the heat treatment. So, we know that when either warm or hot working is carried out, there will be lot of the metallurgical changes which may be undesirable from the mechanical performance of point of view. Therefore, it becomes important to restore the microstructure and improve the mechanical properties. Likewise, especially under the cold working conditions where the mechanical plastic deformation is carried out, and then it is possible like the flow of the grains or the grain orientation is not favorable, grain orientation is not favorable, and that is resulting the undesirable set of the properties in a particular direction, which may be of the great importance from the performance point of view, or this can also lead to the anisotropy. Okay. So, this non-uniform variation, non-uniformity in properties many times lead to the unsatisfactory performance of the component which has been produced. So, this is one aspect. So, in order to take care of the thermal effects and the plastic deformation effects and improve the performance of the component which has been produced by the plastic deformation based approaches, it is required to do the heat treatment, so that the properties and performance of the product can be improved. So, in as far as the improvement in properties is concerned, it can be in various forms. Say heat treatment can be used to improve the corrosion resistance. Okay. Presence of the residual stresses sometimes improve the increases the stress corrosion tendency, or the heterogeneity in microstructure promotes the galvanic corrosion. So, in order to restore the corrosion resistance, it becomes useful to carry out the heat treatment of the formed component. Likewise, if the residual stresses due to the non-uniform plastic deformation of the component has been developed, then they will directly be affecting the mechanical properties of the component, like tensile strength and the fatigue resistance of the component is adversely affected. Therefore, because here say applied stress is sigma A and the residual stress is sigma R, then the net effect in form of the net stresses that can be applied will be equal to this much. So, greater is the residual stresses, then the externally applied stress if magnitude that will be that will be reduced, which means the design stresses will be reduced due to the residual stresses. Otherwise, for a given applied stress, if the residual stresses are high, then the component will fail, because this will be the net stress, and net stress may go beyond the acceptable limits. Therefore, minimizing or eliminating the residual stresses become useful from the mechanical performance point of view. So, efforts are always made through the stress relieving treatments to minimize the residual stresses, whether they are tensile or the compressive type. Okay. The dimensional stability, since the residual stresses develop Okay, and say material has been given particular shape, and if there are residual stresses, okay, so then that will have the tendency to change the shape or change the shape of the component by bending in such a way, by deforming in such a way that the component attains a shape which is not desired. So, that is termed as distortion. So, in presence of the residual stresses, components tend to get distorted. Okay. So, in order to eliminate such kind of the distortion tendency, if the heat treatment is done to eliminate the residual stresses, then that will avoid the possibility of the distortion. Additionally, it will also avoid the change in dimension later on during the machining if required. So, the dimensional stability is enhanced. Mechanical properties are also enhanced because if the cold working is carried out, then the due to the cold working, we know that the hardness is enhanced, yield strength is enhanced, but the percentage ductility is reduced, percentage elongation is reduced, and toughness is reduced. So, the elongation and toughness is reduced, yield strength and hardness is enhanced. So, it is possible, like for a given application we may need the greater elongation and the greater toughness properties. So, we need to restore the properties so that they are suitable for the given application. So, the heat treatment may be needed to soften the material in a way. Sometimes when the hot working is carried out, inappropriate combination of the temperature may lead to the compromise in the yield strength, compromise in the other mechanical properties. So, it may be required to carry out the certain kind of the heat treatment like normalizing, so that the mechanical performance of the component can be enhanced. Okay. So, it is required, like the in the metal forming, it is important to assess that depending upon the kind of metal geometry, the metal geometry of the component and the kind of the mechanical, or sorry, the metal working process which has been carried out, we have to assess what kind of the heat treatment is carried out, so that there will be suitable improvement in mechanical properties, dimensional stability, reduction in residual stresses, and improvement in corrosion resistance. The common metals which are normally subjected to the metal forming, these are like the steel is one of the most commonly used metal in automotive industry, in other general engineering industries, where the metal is subjected to the plastic deformation to give the desired size and shape. Okay. And other pH metals like precipitation hardening metals like the aluminium, copper, titanium, magnesium. So, these alloys are hardened through precipitation hardening, and when these are subjected to the hot working especially, then the precipitates get dissolved. So, in order to restore the mechanical properties, the precipitation hardening heat treatment is needed, so that the component which has been produced through the hot working can, the properties of the component can be restored. Okay. So, we have seen that the metal working leads to the development of residual stresses and change in mechanical properties of the material. Okay. And sometimes under the heterogeneity in terms of the microstructure and mechanical properties. So, these are the important aspects which must be taken care of through the proper thermal treatment of the component which has been produced through the metal working. So, depending upon the conditions which have been used for the metal working, we will require the appropriate kind of the heat treatment of the metal of the component which has been produced through the metal forming processes. Okay. So, now we will see, as far as the need is concerned. Now, this is just in a specific form. All needs in metal form components arise due to the localized thermal effects and localized mechanical effect. Thermal effect means localized plastic deformation and localized thermal exposure which is given. Okay. And whenever it is localized, it causes the localized change in microstructure, localized change in mechanical properties, and development of residual stresses. So, these things bring in the heterogeneity, and we want to eliminate all this heterogeneity, because that adversely affects the performance, mechanical performance, and the corrosion resistance of the component. So, since the metal forming involves the plastic deformation, which in turn leads to the residual stress development, change in mechanical properties in form of the hardness, strength and ductility. This especially happens in case of the cold forming conditions, and this in turn results in the non-uniformity in properties and also the directionality, like the direction in a particular direction metal is subjected to get deformed more as compared to the other directions. Say the rolling is happening in this particular direction, so the strength of the metal will be greater in the roll direction of the rolling as compared to its direction perpendicular to the rolling direction. So, that is called directionality, where the properties of the material in certain directions are better as compared to the other directions, and which may not be favorable from the performance of the component point of view. Okay. So, the one aspect is plastic deformation leads to the during the metal working leads to the non-uniformity in terms of the properties and the deformation and the directionality. Another aspect like thermal effects. So, due to the thermal effects during the metal working leads to the microstructural variation, heterogeneity in microstructure and anisotropy. So, this kind of the variation will be different, especially when the plastic deformation is carried out at room temperature. The extent of variation may be more near the surface layers as compared to that the across the section, but when it is done above the recrystallization temperature, then such kind of the heterogeneity is somewhat limited. Okay, because this will be deformation will be done under the hot working conditions, that is above the recrystallization temperature. So, as I said, the plastic deformation, especially when it is carried out under the cold forming conditions, this leads to the development of the residual stresses, and most of the time it is residual compressive stresses at the surface, and which are considered to be favorable, especially under the tensile load conditions. But if the external loading is compressive, then it will be adversely affecting the performance of the component which has been produced. Embrittlement is another aspect under the cold working conditions. Why? Because it is metal when it is subjected to the when metal is subjected, metal working is carried out at room temperature or below the recrystallization temperature. In that case, there will be increased due to the strain hardening, it will be subjected to the increased hardness, increased yield strength, but a reduced percentage elongation, that is ductility, and a reduced toughness, and this combination is known as embrittlement. Material will not be resisting the impact loads effectively, and that will be promoting the brittle fractures under the impact load. Anisotropy is the another aspect, because under the cold working conditions, surface layers will be affected more as compared to the core regions. So, due to the greater the deformation at the surface layers as compared to that of the core, there will be lot of variation in properties, like it may be like this. Okay. So, here you will see at the surface layers the hardness is much higher as compared to the core region. So, this kind of the variation can be find. Similarly, if the rolling is happening, then the strength of the metal in the direction of the rolling will be much higher as compared to the direction perpendicular to that. So, the non-uniformity in properties of the material in the different directions is termed as anisotropy, and that will be more. So, it is important that residual stress is minimized, embrittlement is minimized, and anisotropy is reduced, and therefore, it becomes important to get the suitable kind of the thermal treatment, like say stress relieving treatment is given by heating from temperature 200 to 600 degrees centigrade for the steels, and say 200 to 400 degrees centigrade for say other soft metals like aluminium and magnesium. Embrittlement is typically observed especially in the low stacking fault energy metals. Okay. And this kind of the because the work hardening is significant, leading to the increased hardness and the reduced toughness. So, this kind of the effect can be minimized through the recovery and the recrystallization. Okay. So, by heating the steels below recrystallization temperature, that will below the lower critical temperature will facilitate the recovery and the recrystallization by eliminating the work hardening effect after giving the desired shape to the component through the cold working or cold forming. Okay. Similarly, because of anisotropy is happening because of the certain directionality in microstructure and the plastic deformation. So, to eliminate this, it is important that if the recrystallization is realized, okay, then this kind of the directionality is eliminated. Okay. So, because the new grains will be formed, new equexed grains will be formed, that will eliminate the variation in properties of the material in particular direction. These effects may not be severe in case of the hot forming conditions. So, at high temperature under the hot or warm forming conditions, if the temperature is not appropriate, then this will lead to the undesirable structure. Now, although this undesirable structure may be in form of the coarse grains or undesirable phases which has been undesirable phases which have been formed. This may be in form of like reversion in case of the pH metals, reversion where all precipitates have got dissolved, okay, and the coarsening of the grains means where coarse grains have been formed. So, this will be leading to the reduced mechanical performance. Thermal softening, that will be the another aspect due to the reversion and recrystallization. So, this kind of the undesirable effects need to be minimized. So, depending upon the kind of the metal system which is being subjected to the hot or metal forming, it becomes important to like say the refined grain structure and realize the desired phases which will help us to obtain the desired set of the mechanical properties, okay, and that can be done only through the controlled heat treatment of the material. Okay. So, a suitable heat treatment has to be identified so that the desired combination of the properties and structure can be realized. So, depending upon the metals, like say for steels, it may be in form of annealing, normalizing, okay, and the hardening or quenching followed by tempering. Okay. In case of the pH metals, we may have to perform T4 or T6 kind of the heat treatment involving solutionizing, quenching and followed by aging. So, which kind of the heat treatment will be carried out, that we will have to see as per the metal system and the kind of the properties that we are looking for through the control of the microstructure. So, when heat treatment is carried out, what we realize basically, it during the heat treatment our microstructure is modified and we are able to restore the phases or realize the phases that we are looking for, and we realize the grain structure. If it was coarse, then it can be refined using suitable controlled heat treatment. Since the residual stresses are usually developed under the cold working conditions and the heat treatment is carried out, then we can minimize or eliminate the residual stresses if these have been developed. But for that, a stress relieving treatment has to be performed, say for steels by heating 200 to 650 degrees centigrade temperature. We have seen that the structure which is usually realized through the metal forming is heterogeneous, different structure in different zones and the different properties, and therefore, for improving the homogeneity, heat treatment is when heat treatment is performed, that helps in homogenizing or bringing in more uniformity in structure and properties of the metal formed components. Okay. All these will help in improving the performance. Similarly, due to the heterogeneity in microstructure and mechanical properties, we will see lot of variability in the different directions in terms of the properties and structure, and this has to be eliminated. And so, when heat treatment is carried out, anisotropic nature of the characteristic of the metal formed component is minimized. Similarly, the allows further heat treatment. You see, there is one particular heat treatment which is called in process annealing. In process annealing. Okay. So, say the metal working may be carried out in the different stages like this. Okay. So, stage 1, 2, 3, 4, 5, and after each stage metal is subjected to say cold working. Okay. So, the increasing cold working successively in the different stages, this will be causing the increased hardness, reduced ductility, and increased hardness, reduced ductility, increased strength will be making the deformation further difficult. It will be increasing the tendency for cracking. So, in order to make the material further deform, in order to induce the deformation capabilities further without getting cracked, it becomes important to do the in process annealing in between the different stages of the deformation, so that the ductility, that is the percentage elongation, can be induced and material can be softened by reducing the hardness and yield strength, and this happens due to the recovery and recrystallization, wherein the work hardening effect is eliminated. Okay. Say for an example, steels allow significant change in properties. Why? Because whenever steel is subjected to any kind of the thermal or heat treatment, it allows change of phases as per the need. Say soft phases like ferrite and the pearlite, relatively soft phases like ferrite and pearlite, these can be transformed into the variety of phases, like it we can get the benite, we can get the martensite, or even the mixture of like martensite plus ferrite in case of the dual phase steel, or the varying sizes like fine pearlite or mixture of the coarse and fine pearlite. So, we can have a variety of combination of the structures in order to regulate the properties as per the requirement. So, this is the kind of ability of the ferrous metals which allows the change in microstructure by applying the suitable combination of the thermal treatment. Once the structure is changed, then we get the properties accordingly. Okay. So, that is the benefit of the steel and application of the thermal treatment of the steels. So, steels allows the phase transformation based on the application of the suitable thermal cycle, that is like controlled heating and cooling. The kind of heating cycle that we use is like this. So, first heating like temperature in y axis and time in x axis. Okay. So, heating, then holding it at a high temperature for sufficient time. This temperature is very crucial. So, this time is called soaking time, and this you can say as a peak temperature. We hold it depending upon the purpose, we hold it at high temperature for sufficient time. Okay. So, this high temperature or peak temperature depends on the kind of heat treatment which is to be carried out. Say for not annealing, for normalizing and for hardening, what we do, we heat it above the upper critical temperature of steel plus 30 to 50 degrees centigrade higher. Okay. So, that is how the upper this peak temperature is identified. Thereafter, once the sufficient soaking has been done at this high temperature, what we do, we try to identify the suitable cooling rate to be used. Okay. So, after this soaking, we need to see really at what rate it should be cooled. So, it can be cooled very slowly like 2 to 5 degrees centigrade per second, or it can be cooled a little faster like 30 to 40 degrees centigrade per second, or it can be quenched rapidly like 100 to 200 or 500 degrees centigrade per second. So, accordingly here we will be getting the different phases. So, steel initially had pearlite plus ferrite at the room temperature. Okay. When it was heated to the high temperature for these three heat treatments, what we have got, homogeneous austenite, and this homogeneous austenite is subjected to the cooling at different rates. Okay. When it is cooled at different rates, what we get? We get the coarse pearlite on slow cooling, fine pearlite on fast cooling, and the and we get the martensite on extremely fast cooling. So, the very slow cooling is carried out for the annealing heat treatment, resulting in the softness, induces softness, reduces the strength. In this refines the structure. A little fast cooling for normalizing. This refines the grain structure, improves the mechanical properties and toughness, and the austenite transforms into the martensite, leading to the hardening. Significant increase in the hardness, increase in yield strength, but reduced toughness and ductility. So, this kind of the property variation can simply be realized through the thermal treatment, okay, for these three heat treatments. But for the stress relieving, what we have to do, if this is the lower critical temperature above which steels experience the phase transformation, then we have to heat the metals below the recrystallization temperature, like say this may be from 200 degrees centigrade to 650 or 700 degrees centigrade. Okay, and this is the temperature. So, we heat it like this, hold it, and then air cool later on. Okay. Since there is no phase transformation, whatever structure it had, it will remain in the same way, but this kind of the heating, soaking and followed by air cooling will relieve the residual stresses which were there. So, this kind of the heat treatment is known as the stress relieving heat treatment. Okay. And the same thing is done for the in process annealing to eliminate the work hardening effect through the recovery and the recrystallization, so that the ductility can be induced for further processing of the metals. Many metals like aluminum, titanium, copper, magnesium, these during the hot forming, these suffer especially in terms of the softening due to the reversion effect. What is that reversion? A metal initially will be having lot of precipitates, because of which it would be getting its strength, but when it is subjected to the hot working, then all these precipitates get dissolved, and once these get dissolved, then metal becomes soft, and in the dissolved state metal will be subjected to the plastic deformation at high temperature, and the desired shape will be given. But since it is having the absence of there are no hardening precipitates, so it will be soft, it will be of low strength. So, it is important that the desired precipitates are restored through the suitable heat treatment. Okay. And that for that heat treatment, we have to carry out the precipitation hardening heat treatment of these metals, because precipitates get lost. And why these get lost? Because of the reversion, that is the loss of precipitates, coarsening of the grains because of high temperature exposure at the high temperature exposure for longer time, degradation in mechanical properties because of the reversion and coarsening, and the loss of corrosion resistance because of the heterogeneity in structure. So, it becomes important to do the precipitation hardening heat treatment of the metal. So, there are three main stages in precipitation hardening heat treatment of the metal, like one, similar to the earlier one, heat it, hold it for some time, this is called solutionizing. During this solutionizing, all phases, all precipitates which are present in the alloy in pH metals, all these are dissolved, followed by rapid cooling, this is called quenching. Okay. In quenching stage, so here we have got the homogeneous solid solution. Okay. And here in y axis we have temperature, and axis we have time. Okay. So, this is thermal cycle, typical thermal cycle which is used, and then the homogeneous solid solution, then when we quench it rapidly, then on quenching we get the supersaturated solid solution, supersaturated solid solution at room temperature. Now, we are left with the two options, either reheat it to somewhat a little higher temperature, or leave it at room temperature. So, supersaturated solid solution, when left at room temperature, it starts aging slowly. Okay. This slow aging results in the T4 heat treatment, T4 tempering. If the heating, it is reheated, say depending on the metal, if it is reheated to the higher temperature, say 150 to 200 degree centigrade, and held it for some time, followed by air cooling, then this will be leading to the artificial aging. So, our natural aging is one where after quenching, the component is left at room temperature for aging on its own. This takes very long time to achieve the desired precipitates, achieve the desired strength in the metal formed component. But if we do the artificial aging by reheating the component to the little higher temperature, say 150 to 200 degree centigrade, then this kind of the aging will be happening very fast. Otherwise, natural aging may take days, weeks, even months, but artificial aging may take like say 4 hours, 8 hours, 10 hours, 12 hours, like that, and it will achieve the, it will give you the desired strength. Okay, and induce the desired phases. So, these are the three stages: solutionizing, that is this, quenching, that is this for developing the supersaturated solid solution, and aging is one where the desired precipitates will be restored either by reheating to the little higher temperature for T6 heat treatment, or by leaving it in the room temperature for natural aging through the T4 heat treatment. Okay. So, this is just a summary, like the heat treatment after hot rolling, steel sheets and plates may undergo heat treatment processes like annealing, normalizing, quenching, tempering to enhance the properties, and these treatments modify the microstructure, affect the hardness, ductility and other desired characteristics. So, that is what summarily happens. The typical heat treatments like annealing, where heating is done to the specific high temperature, which is basically 30 to 50 degree centigrade plus the upper critical temperature. Okay, in case of the carbon steels or the steels, followed by slow cooling to soften the material and reduce the residual stresses, that is the annealing. Normalizing, heating to the high temperature above the recrystallization temperature, above the upper critical temperature, by 30 to 50 degrees centigrade above the upper critical temperature, followed by air cooling. So that little higher cooling rate will be leading to the fine grain structure and improved mechanical properties, okay, with the improved uniformity in properties. Quenching is about rapid cooling from the austenitic state, means the heating to the temperature above 30 to 50 degrees centigrade above the upper critical temperature, followed by rapid cooling to produce the martensitic structure, so that the hardness and the strength can be enhanced, but it leads to the brittleness because of the reduction in toughness of the metal. Few other heat treatments are like tempering. So, after the hardening we get the significant increase in hardness, but reduced toughness. So, we have to induce the toughness. So, reheating after hardening, reheating the steel after quenching to little lower temperature, that is below the lower critical temperature, followed by slow cooling, increases the toughness and reduces the brittleness. So, that is what we see. If tempering temperature is like this, tempering temperature in x axis, hardness or toughness in the y axis, then hardness comes down like this with the increase of tempering temperature from 200 degree centigrade to say 700 degree centigrade in case of carbon steels. On the other hand, toughness goes in like this. So, hardness and toughness go in opposite manner. So, depending upon the combination of the properties that we are looking for, choose the suitable tempering temperature, so that suitable combination of the toughness and hardness can be restored. Okay. Case hardening especially used when we want the harder surface layers while the core is still tough and soft. Precipitation hardening heat treatment I have just described, inducing the precipitates within the material to enhance the properties. And sometimes in case of the low carbon steels, if the component is having the lower strength and lower hardness at the surface, then carbon content at the surface is enhanced, followed by the quenching heat treatment for increasing the surface hardness. So, purpose of the heat treatment is, there are so many purposes, as I have said: improving the mechanical properties, improving the microstructure, stress relieving and dimensional accuracy. After heat treatment, we can see that heat treatment helps in stabilizing the dimensions after the cold rolling. There are multiple factors that affect the kind of heat treatment, the kind of temperature, soaking time, cooling cycles to be used. One is the material composition. So, the chemical composition of the steel, including the presence of alloying elements, affect the response to the heat treatment, because it directly affects the upper critical temperature, lower critical temperature and the critical cooling rate, as these are obtained through the continuous cooling diagram and iron carbon diagram. So, composition and alloying elements affect the kind of temperatures to be used for the heat treatment purpose, and additionally these affect the response to the heat treatment, because the hardenability is affected by the presence of these elements. Then the desired properties. Okay. Depending upon the kind of properties that we are looking for, we have to use the suitable kind of the heat treatment. Whether it is softness is to be induced, then we will be doing the annealing. If we want more strengthening, then we will be doing the normalizing. If you want just hardening, then the quenching treatment is to be used. Heating and cooling rates then accordingly are designed as per the need of the microstructure to be induced and the kind of properties that we are looking for. Holding time for which the material has to be held for at a high temperature, that will depend upon the certainly composition, section thickness, okay, to realize the uniformity in the microstructure that is being produced at a higher temperature, whether it is solutionizing or austenitizing. Okay. So, depending on the composition, section thickness, the time is affected, soaking time is affected. I will be talking a little bit in detail about these aspects. Say, how to design a heat treatment either for normalizing or annealing or heat treatment. So, designing of heat treatment involves these three aspects: selection of suitable peak temperature, soaking time and cooling rate to be used. So, typical heat treatment cycle which is used is heating, then holding at a high temperature, followed by cooling at different rates. Slow cooling for annealing, little faster cooling for normalizing and fastest cooling for the hardening or quenching treatment. Okay. So, as far as for steels, for plain carbon steels, we have to use iron carbon diagram. For identifying the peak temperature, what we do for heat treatments like annealing, normalizing and quenching, what we do? We heat the steel component or the component 30 to 50 degrees centigrade above the upper critical temperature, and which is the function of the composition. You can see here, Okay. So, heat it above the based on the composition, select the suitable upper critical temperature and then go little higher by 30 to 50 degrees centigrade above that. Hold it at this temperature for some time, but for how long? Soaking time will depend upon the composition. If it's alloy steel, then it will take longer than the carbon steels. Why? Because alloy steels will have alloy carbides, while the carbon steels will have only ferrite and pearlite. So, initially when steel is heated, it shows the relationship between the temperature and time to realize the homogeneous austenitic state. Higher the temperature, shorter the time it takes. Lower the temperature, longer the time it takes to realize the homogeneous austenitic state, that is the austenitic state. So, these are the two aspects. High temperature reduces the soaking time, okay, and carbon steels take lesser time as compared to that of the alloy steels to get the homogeneous austenitic state. Once we have got the homogeneous austenitic state, next thing is to see what will be formed at what cooling rate. So, this is the CCT diagram, that is called continuous cooling transformation diagram, and this is the triple T diagram, or also known as isothermal transformation diagram. Isothermal transformation diagram simply shows that what austenite will be forming when it is held at a constant temperature. So, like say at a higher temperature it will be forming the coarse pearlite, little lower temperature austenite will be forming fine pearlite, and further finer pearlite will be formed when it is held at further lower temperature. But further lower temperature, when austenite is held, it produces the coarse bainite. Further lower temperature results in the fine bainite. Further lower temperatures, it results in the like combination of the austenite and martensite. And when the quenching is done, directly quenching is done at the temperature below the MF temperature, then it will be producing the martensite. So, austenite forms the martensite directly when it is quenched in a bath kept below the MF temperature. So, these are the isothermal transformation thing. If we are doing the cooling continuously instead of the isothermal, then we have to see that on slow cooling what we get, coarse pearlite. On fine little faster cooling we get the fine pearlite. Further faster cooling we will get the combination of the pearlite and the martensite. Further faster cooling will result in the martensite and martensite. So, this critical cooling rate, the green line, what it shows, that minimum cooling rate that we need to impose to transform the austenite completely into the martensite for the hardening heat treatment. When we do the hardening heat treatment at the surface, we develop the tensile residual stresses, while at the core it is compressive. Since the surfaces get hardened, so presence of tensile stresses and increased hardness increases the tendency of cracking. So, in order to reduce the residual tensile stresses and reduce the cracking tendency, it becomes important to do the eliminate the these residual stresses and induce the toughness by inducing the suitable combination of the phases. So, that is what we see here. The thermal cycle typically used for the quenching is like this: the heating, austenitization, followed by rapid cooling for the hardening purpose, then reheating, okay, reheating 200 to 600 degrees centigrade below the recrystallization temperature, and during this only the tempering will be happening. When the tempering happens, this is what we get. On tempering, increasing the tempering temperature decreases the hardness of the carbon steel, okay, but on the increasing the tempering temperature, it increases the toughness. So, we have to select the suitable combination of the tempering temperature in such a way that we are able to achieve the desired combination of the properties. Stress relieving is the another aspect. Like as I have said, the lot of residual stresses develop in the metal forming during the metal forming. So, if we give the high temperature exposure for some time, then residual stress magnitude is reduced, because locked in strain is relieved when the metal is softened due to the heating or due to the heat applied. So, when we heat, metals yield strength is reduced, and that in turn relieves the locked in strain. Okay. So, if we expose at too high temperature, say 620 degrees centigrade, then the relieving of residual stress is so fast, so quick, in just 15 minutes almost, like say most of the residual stress is relieved. But if we go with a little lower temperature, say 480, it will take little longer time to reduce the residual stresses, and the extent of reduction will also be limited. The 260 and 370 degrees centigrade will be reducing the residual stresses, but not much. Okay. So, this is one aspect. So, here we can see directly the effect of the tempering the effect of the stress relieving temperature, say from 300 degrees centigrade to the 700 degrees centigrade, and what happens when it is held for short time, little longer, and very long time. So, residual stress magnitude which is left, like stress getting relieved, 100% stress relieving is happening when it is held at a longer time, at higher temperature for longer time, 6 hours. Okay. So, for any tempering temperature, increasing the holding time reduces the kind of relieves the residual stresses which are there, or for any particular time, if we see increasing the stress relieving temperature will simply be reducing the residual stress level. Okay. So, it is important to identify suitable combination of the temperature and time for stress relieving. If you want to relieve the residual stress significantly, then we have to go close to the lower critical temperature. The heat treatment of the pH metal is the another aspect about which I have talked a little bit, like it has there 3 stages: solutionizing, which involves like suitable combination of the temperature and time, and then quenching for developing the super saturated solid solution, and then aging. Okay, artificial aging or natural aging. So, this is what is done, like this is an example of like aluminium and copper. Okay, in aluminium copper combination, say this is a particular combination of the alloy. So, we heat it to the high temperature like this, so that every alloy copper gets dissolved into the aluminium matrix. Okay. Then from here we develop the solid solution, homogeneous solid solution. Then from here we cool it rapidly, so that by the quenching super saturated solid solution is developed. Then we do the reheating. Okay. So, these are the cycles: solution heat treatment by heating to say temperature like this 550 in this temperature band, say for aluminum copper combination. Once the homogeneous solid solution is developed, say depending upon the kind of the method by which the metal has been produced, whether it is by casting, it will take long time; by forming, it will take short time, depending on the grain size and method of manufacturing. Okay. Still it may vary from 1 to 4 hours for developing the homogeneous thing, followed by rapid cooling to develop the supersaturated solid solution, then again reheating. So, reheating is used for artificial aging, during which precipitates will be formed, followed by air cooling, or it is left at room temperature for natural aging. So, this will take very long time. So, if we try to see the aging curve which shows the variation in properties as a function of the time. So, here we have the say hardness. So, when the aging is done at room temperature slowly, it can take days or weeks or months to attain the high hardness, that is this. Okay. So, it takes time, it takes very long time to achieve the peak hardness. This is a peak hardness, right, peak hardness. So, below this you see any time during which, any time when the precipitation is incomplete, that is known as underaged condition. This is the incomplete aging condition, and if we continue to hold it further longer time, then it will be subjected to the over aging. Okay, over aging. So, we have to age the things corresponding to the peak hardness. Okay. So, if we do the aging at higher temperature, then it will show curve like this, like say the hardness here, time here. Okay, and this will be happening, say this is happening at say 150 degrees centigrade, 150 degrees centigrade and 200 degrees centigrade. Okay. So, at 200 the peak stage is achieved earlier. This is the aged stage, this is the overaged state. Similarly, the curve which is taking the aging is done at little lower temperature, then it will take longer time to attain the peak hardness level. So, this variation in the hardness as a function of time during the aging is known as aging, and during this stage precipitates will be developed which will be offering the desired increase in strength of the material. Okay, now I'll summarize this presentation. In this presentation basically I have talked about the need of the heat treatment in the metal forming, what kind of the adverse effects in terms of the microstructure, mechanical properties, anisotropy that are observed in the components produced by metal forming, especially under the cold conditions. Then how through the heat treatment we can reduce the adverse effects related with the metal forming, and how we can restore the properties and microstructure and relieve the residual stresses so that the performance of the product can be enhanced. Thank you for your attention.